Welcome to the graph analysis practice tutorial. We are going to start by asking and answering what is the purpose of a graph in science. And actually there are several purposes, but primarily we're trying to visualize the data. A lot of people can see data more graphically in a graph form, have a hard time interpreting it necessarily right from a data table. So we can see what's going on more clearly often in graphs than in data tables. It helps us to see patterns in the data more clearly and more graphically. So just as a picture is worth 1,000 words, a graph is worth 1,000 data points. And besides, some people think graphs are just pretty. Okay, so if we look at this first graph, as you approach a graph, the first thing you want to do is read the title. Comparison of temperature scales. So we're comparing two temperature scales, the Fahrenheit scale with the Celsius scale. And then we're asked to find different data from this graph. So find the Celsius equivalent of 70 degrees Fahrenheit, which is roughly a good room temperature. So if we find 70 degrees Fahrenheit, first thing we have to do is find the 0 points, the origin. Here's 0 Celsius, here's 0 Fahrenheit. So it is actually possible to get below 0 on both scales. Then we have to calibrate or figure out what the calibration is for each of the graphs. So if 0 starts here and 100 is there and there's 5 spaces in between, then each space counts for 20. So 20, 40, 60, 80, 100. If this is 60 and this is 80, and 70 is going to be somewhere in between. So then if you just extend it over and extend it down, then we can read that the degrees Celsius equivalent would be roughly right here. Now these lines are 20 each, but here from 0 to 50 with 5 spaces, each one counts for 10. So we would read 10, 20, and a little more than 20. So we would have to estimate that it's approximately 22 degrees Celsius. Now, what about the Fahrenheit equivalent of 70 degrees Celsius? So we find 70 degrees Celsius, trace it up, and then trace it over, and then 100, 120, 140, not quite to 160, so estimate about 158 degrees Fahrenheit. Now, what about human body temperature? 98.6 Fahrenheit. What would that be in Celsius? So if we take 98.6, almost to 100, trace it over, trace it down, and then 10, 20, 30, not quite to 40, so approximately 37 degrees Celsius. What about if we're baking cookies? 350 degrees Fahrenheit, what would that be in Celsius? So 300 here, 320, 340, 350, trace it over, and then trace it down. And it's off of your screen, but I can see it on my screen. So 150, 160, 170, not quite to 180. So we would estimate about 177. Okay. So one of the things you can do with graphs is just glean information, comparing this axis to this axis. Okay. Next graph. Read the title. Here we're comparing pressure and temperature. So we're analyzing data from some gaseous substance. And when we change the temperature, which you can't read, it's off of your graph, but I can see temperatures on the x-axis and pressure is on the y-axis. Pressure is in millimeters of mercury, temperature is in degrees Celsius. So how does the pressure of the gas change with temperature? Well, if we follow the line, you can see that it has a positive slope, which means as the x changes, it's increasing from low numbers to high numbers as we go up the line. And what's happening to the y numbers? Well, they're also increasing, going from lower numbers to higher numbers. So that's how we would describe it. As the temperature increases, the pressure also increases. So what math term applies to this? Is it a direct relationship or an inverse relationship? Well, inverse means that they're kind of opposite. As one increases, the other decreases, or vice versa. But in this case, both are increasing. That would be a direct relationship. Now, next question. What temperature is the gas? The pressure is 822 millimeters. There's 800. There's 900. 5 spaces. So each space counts for 20. 800, 20. Over. Trace it over, trace it down. And we would get somewhere not quite to 50. So approximate 47 degrees. What is the temperature of a gas what is the pressure of a gas at temperature 0? Now, some students get flummoxed by the fact that the line doesn't extend that far. But imagine if we had taken the data. Where would the data be? So we can extrapolate the line down, which is a tool that we use frequently. And if we do that, we can see that the pressure would be roughly 700 millimeters of mercury. Okay, next graph. We're examining the mass and volume of two different substances and the relationship between mass and volume. Substance A, substance B. Mass is on the y-axis, volume on the x-axis. So what would the mass of 60 milliliters of 60 millimeters sample of substance B? So we have to find 60 milliliters, which is right here. Trace it up. And then for substance B, trace it over. And then what about for substance A? Trace it over. So we could approximate this is a little over 20, and this is a little less than 70. Okay. What if we want to know the volume of a 75-gram sample of substance B and substance A? Okay. So we have to find 75 grams. It's up here. Trace it over, and right away we see we have a problem, don't we? Substance B, the line would continue, and we're way off the graph. So I'm going to have to show you that skill a little bit later in class. But for substance A, we can clearly see right here that it's not quite 70, a little more than halfway between 60 and 70, so 66 milliliters. Now, what about the slope for a line? Everybody knows slope is how steep the line is. Okay? But we want to be able to quantify that and see what that tells us. Okay? So change in y over change in x. Now some students get thrown if there aren't points drawn in on their graph. So what you can actually do is just pick 2 points. I like to pick 2 points that are directly on the line for the y-axis. Okay, so if we just pick 30 and 10, how much of a change is that? 30 grams minus 10 grams will give us 20 grams. So for substance A, as it changes from 10 to 30, that's a change of 20 grams. How much does the volume change for that same change in the substance? So all you have to do is what we did before. Trace the line over and trace the line down for each of the data points. So for 10, we can see it's not quite to 10. And for 30, we can see that it's a little more than halfway to 30. So somewhere around 27 minus 9. So as the x-axis changes 20 grams, as the y-axis changes 20 grams, the x-axis changes only 18 milliliters. So if we divide those two numbers, 20 divided by 18, we get 1.1. And if we divide grams by milliliters, they don't divide out. So we read it this way, grams per milliliter. So this thing has a mass-volume relationship of 1.1 grams per milliliter. What about for substance B? Change in y, let's use the same 2 data points. 30 minus 10. So for every 20 gram change substance B, we can see there's quite a bigger change in volume. Okay? So it takes a lot more of substance B to change its volume. So if we trace 30 down and 10 down, we can see that there's a much bigger change in volume. We read this one, it's about halfway between the 80 and 90, and this one is not quite, a little more than halfway, between 20 and 30. So 85 minus 27 gives us 58 milliliters. So 20 divided by 58 is 0.34, and grams divided by milliliters is grams per milliliter. Now, the next question asks something kind of odd. It says, what's the meaning of the slope for these lines? And I remember being in your chair wondering, what do you mean, what does the slope mean? It just means how steep the line is. Okay? So how can slope mean something else? Well, in science it can. If it's change in y over change in x, mass over volume, let the units tell you something. What is mass over volume? Mass over volume is a substance density, right? So in a very real way, this line represents the density for substance A, and this line represents the density for substance B. So which substance is more dense? Well, which one has a greater density? Substance A's density is 1.1, substance B is 0.34. So clearly substance A is more dense. It has more mass for the same volume. Okay, so if we say volume of 20, there's much greater mass in A than in B. Now, if the density of water is 1, which substance would sink and which would float? Well, in order to sink, a substance density has to be greater than 1. And substance A's density is 1.1, just barely greater, so substance A would just barely sink. And substance B would float quite significantly because its density is only 0.34. So hopefully this graph analysis practice has helped you figure out how to interpret graphs a little bit better.